This is joint work with Jack Grigg and Dara Hopwood, who are also my coworkers at the Electric Coin Company. So the current progress of Halo is that we have a paper out. It's on ePrint. It is not very formalized. There's no security arguments or anything like that right now. It's actually quite a bit out of date. I need to go home and push some things to it, but and it's a work in progress. But it's not really a shot in the dark. It's most of the ideas are pretty grounded in existing protocols, existing concepts. So to me, there's nothing new, and there's not very many barriers in the way of actually getting formalization and security arguments, especially with all these new papers coming out that are creating frameworks for helping analyze and communicate these ideas. So we actually have an implementation. So alongside the paper, we posted an implementation. It's not just like a work in progress one, sort of, because it really does work. You can create recursive proofs with it. We have a little demo where it recursively proves that a Bitcoin block hash is the result of like after 10 blocks or something like that. It goes to a depth of 10, so it works, but it's pretty slow, and I'm in the progress of making it a lot faster, so I think it'll be like 5 or 8 times faster once I get around to pushing the code. So to kind of motivate what's going on here with Halo, let's imagine that you have a computation and you'd like me to run it for you. So what you could do is you could split it up into a bunch of different steps. And then in each step, I could give you a proof that performs some state transition that corresponds with the step for the computation. And then I give you all these proofs, and you check them, and now you're convinced that I performed the computation so far correctly. And I can continue this on, and if the computation doesn't stop, for example, if it's checking a blockchain or something like that. But obviously, one of the major downsides of this, of course, is that I have to give you a proof every single time, and if I give you a proof, I need to give you all the previous proofs so you can check them. So although this is iterative and it's quite nice, it's not succinct in that sense. So you can't really create what we know as a succinct blockchain, for example, using this. So what we need is a proof that can verify another proof. So for example, in this little diagram here, we have a proof 2, which checks proof 1 as part of its verification circuit, in common parlance. And so it's responsible not only for checking proof 1, but it also checks to see if the state transition between state 1 and state 2 was correct. And proof 3 goes on to take proof 2 and check that. And so in the end, you can keep doing this over and over, and ultimately you only have one proof that you check, and that it sort of inductively proves or verifies all of the proofs that are nested underneath it, which is great, and this is kind of forms the foundation of a succinct blockchain. There's 2 problems. One is that in practice, obviously, creating proofs that are really efficient to verify inside of these circuits are really difficult, but we have new proving systems. We have SNARKS, so that's something that we've begun to solve. And then the other problem is that usually the verification procedure has to be expressed in a language that the proving system itself can efficiently reason about so that it can actually verify it. So this is something that you can solve, for example, just as a quick example, is something that was done in the ZEXE paper, where you have, so we create 2 proving systems, 2 pairing-based SNARK proving systems built on 2 separate elliptic curves. So we have this BLS12 curve that's about a 377-bit curve, and then it is embedded within another curve that's created using the Cox-Pinch method. And the relationship between these 2 curves is that the scalar field for the Cox-Pinch curve is the base field for the BLS12 curve. And so the Cox-Pinch curve can be used to efficiently verify or perform group arithmetic and target group arithmetic and so on. All this arithmetic you have to do as part of the pairing function efficiently for proofs that are created using the BLS12 curve, and then you can use the BLS12 curve to also create SNARK proofs. So this is kind of an example of a fixed depth proof composition. So you have a depth of 1, which is useful for ZEXE because that's all it needed was a depth of 1 for what it was doing. But this doesn't scale. I mean, if you want to do another depth, you'd have to create another curve, and these curves get larger and larger. So this doesn't really work. But this has been solved before, many years ago by Elie Ben-Sasson and Alessandro Chiesa and Laurent Tremere and Medeiros Verza back in 2014, where essentially we take a cycle of curves that are both pairing friendly, that have, it's the base field of one is the scalar field of the other and vice versa. We only know of one way to construct cycles like this, and it's using these special MNT curves with very low embedding degrees, and so as a result, the bit sizes need to be pretty large to compensate for the security loss. So what does that mean? Well, there's a few different downsides. One is that the keying material is large, not symmetric, but like asymmetric keys, like elliptic curve points and things like that. Depending on your protocol, that's not really ideal. A little bit worse is the fact that the larger bit sizes mean that the multi-exps are slower, the scalar multiplications and FFTs and all this stuff are much more expensive. Proof sizes become larger, blah, blah, blah. But even worse is that it requires a trusted setup. And a trusted setup for each curve, and also up until recently for each circuit. But this is something that we've begun to obviously fix. So it's beginning last year with Grott and the others, Mary Maller and so on, had a paper that introduced the concept of updatable and universal SNARKs. And then Sonic, which was earlier this year, which kind of introduced the first actual practical example of such a proving system. And then obviously we've heard today about Planck and Marlin and all these other approaches that are improving on Sonic. Now, the interesting thing to note about Sonic is that Sonic isn't just a SNARK. So it actually didn't start out as a SNARK. It only became a SNARK in the last month because we really wanted to call it a SNARK so it would get accepted at the conference. So we came up with a way to make it a SNARK. So that's kind of the accident that really happened. So Planck and Marlin are really improvements on the fully succinct version of Sonic. But before we had come up with that, we actually had this only amortized succinct version of Sonic. And so I'm going to go into detail about what that means here in a second. So you've heard about polynomial commitment schemes 100 times today. They allow you to commit to a polynomial. You can evaluate the polynomial at a point and then prove that you did so correctly. And then we have these succinct polynomial commitment schemes, which are essentially the commitments and the proofs and the verification procedure are all really fast, usually using Kate's scheme. They're constant in the degree of the polynomial, so these are really great for creating SNARKs like Sonic and Marlin and so on. So I'm not going to really be talking about succinct polynomial commitment schemes today, not very much. So I'm just going to focus on just a normal polynomial commitment scheme. This isn't a really formal description. You need to be able to extract the polynomial, and you want hiding properties and stuff like that. But I'm just if you're curious about a formal description, some of the previous talks did a better job of that. So I'm going to talk about the core protocol of Sonic real quick. If you want to learn about how Sonic works in detail, I have a talk that I did at ZCon 1, which actually goes over all the arithmetic, which I'd invite you to watch. So to start the prover and verifier, this is an interactive protocol, public coin interactive protocol. The prover and verifier agree upon this polynomial k, which is used to encode the public inputs, the statement that's being proved. And the prover starts by committing to this polynomial r, which encodes the witness or the auxiliary inputs of the circuit. And then the verifier replies with a challenge y. And the prover responds with two polynomial commitments, one to this polynomial t, which I'm not going to go into why or what it does. It's essentially used as part of the argument to prove that the constraint system is satisfied with the circuit. And another polynomial commitment to this polynomial s. And so actually the verifier needs to check to see if these polynomial commitments are to the correct polynomials, which it does here in a second. But this polynomial s is important. It encodes the circuit. And so we're trusting, at the beginning, we're trusting, or we want to check to see if the prover actually committed to the correct polynomial that encodes the circuit, where y is fixed but x is unknown. So in the next step, the verifier replies with this challenge x, and then we checked a few things using the polynomial commitment scheme. First off, is the constraint system satisfied? So we established this, it's a technicality, but we established this by checking that the commitment to the polynomial t has a constant term of 0, and this is something actually the polynomial commitment scheme gives you for free in our case. We also have to check to see if this R polynomial is degree bound at a particular degree. Again, a technicality I'm not going to go into. But then we proceed to check these commitments that the prover sent in the previous round. So we check to see if the T commitment is correct. And so essentially we use the polynomial commitment scheme to query these polynomials. And then we check to see if some identity holds, and then we're happy with that. The real trick at the end of this, so everything before this is actually, at least in Sonic, is really inexpensive to do. The hard part at the end is the commitment to this S polynomial correct? So did the prover really commit to the correct polynomial that encodes the circuit? So in Sonic, we had two approaches. One was a fully succinct approach, which was really slow, and people have been improving on it with like Marlin and Planck and so on. But then there's a second approach, which is actually really cool, where if you have this third-party, untrusted third party called a helper, which is willing to construct an advice string for you using the proofs, they can convince you that a batch of proofs, many proofs, are correct, and that this relationship, that this polynomial commitment to this S polynomial is correct for each one of these proofs. They can convince you with the same amount of effort that it takes to asymptotically to check for one of these proofs. So this is really cool, and so we call this amortized succinctness because essentially we're making it so the cost of verifying a bunch of proofs is about the same cost as verifying one using an external help. So how does this amortized succinctness work? Well, okay, like I said, each proof has a commitment or an alleged commitment to this S polynomial, evaluated at the different Y's that correspond to the challenges for each one of these protocols. And we want to check to see if each one of these commitments is correct. Now, we could use linear work to check each one of them using some protocol. But instead of doing this, we perform an interactive argument where the verifier with the helper, where the verifier sends this challenge X, and the helper responds with a commitment to this polynomial S, the same polynomial. All these proofs use the same polynomial because they're based on the same circuit. It's the same polynomial but with X set but Y unknown. And we proceed to use the polynomial commitment scheme to evaluate the commitments that are adjacent to the proofs, as well as the commitment that the helper provided at the points to check to see if they agree. And if they do, and if the polynomial commitment that the helper sent is correct, this one that I've highlighted in red here, then with high probability the original commitments that are adjacent to the proofs are also correct. And so now I only have to perform a linear amount of work to check that this last polynomial commitment is correct. So that's kind of the amortization procedure. So I'm going to kind of abstract what just happened. Basically, the proof had some value in it, and the prover claimed that that value is the output of some function over some inputs. And we had some strategy for taking a batch of proofs that have similar values, but using different inputs, but all over the same function, and we amortized it so that the verifier could be convinced that all three of these values, V1, V2, and V3, were correct, as long as this fourth value, V4, is correct. So this amortization process is kind of one of the core components of the technique that we use in Halo. So the actual core component of Halo is this thing called nested amortization. So let's take an example where, let's say we have a proof. Proof 1, in order to check the proof, I'm just a computer or a human being, I'm checking this proof. I need to perform this expensive operation F over some input that's usually a challenge or something like that from the verification of the proof. So okay, that sucks. Now, when I want to nest the proof verification, this gets tricky. So instead of proof 2 checking the proof 1 completely, which would require the proof 2 to verification circuit to actually encode the entire procedure F in it, which would be expensive and would be linear time, because this is basically representing a linear time operation. Instead of doing that, the prover provides the value instead. So here, actually, let me make sure that I'm explaining the correct slide. So Okay, so the basic idea is that the prover is going to witness the correct value of the output of this function f. They're not going to compute it inside the circuit. They're going to witness it. They're going to claim that that's the correct value. And then as public inputs, we're going to shuffle out the inputs and the outputs of this function. And outside of the circuit, the verifier is responsible for not only verifying proof 2, but also for verifying these additional values that were shuffled out as public inputs. So the trick is when we get to proof 2, and this should actually say proof 1 there, but when we get to proof 2 and we want to check proof 1, we have a problem inside of the proof 2 predicate, the circuit. It not only needs to check proof 2, which will involve running this f function over a new input, but it will also need to check the inputs for that I just spoke about that are the public inputs for proof 1 that were deferred that proof 2 is responsible for checking. So this is where the amortization procedure comes in play. Essentially, instead of performing these two checks, which are linear time, we run this amortization process, and then this produces two new values, one value that's witnessed by the prover, that's the output of the function, and the input to the function, and we export that as public inputs. So instead of, in the previous slide, instead of just returning 4 outputs, 4 public inputs, or whatever you want to call them, to represent the checks that need to be checked, the linear time checks for the inner proofs, we combine them in each step of the recursion, or each step of this nesting process, so that you only ever have to check one. And so outside of the circuit, the verifier has to perform this check. And this keeps going on and on. So proof 3, when it checks proof 2, it takes these two values, the public inputs, and it amortizes them with the values that are created when it checks proof 2, and so on. So this is a kind of an image that better captures what's going on. It's essentially the same thing as the previous slides. It just shows that the proof at any given time is given the amortized information from the previous proof. It performs a verification procedure on the previous proof, and now it runs an amortization operation between those two values to produce a new value that it exports as a public input. And it just continually does this, and so the verifier on the outside of the circuit only needs to check this once. So the consequence of this is that the recursive proof doesn't grow in size, and it doesn't increase in verification time, regardless of how deep this nesting goes, how deep the recursion goes. So the first thing that we can do with this technique, this nested amortization technique, is we could, for example, we could build Sonic on top of the MNT4, MNT6 cycles, the ones that, for example, Coda is going to use. We can use this nested amortization technique to make it so that we don't have to perform the entire succinct verification inside of the circuit. We perform it outside of the circuit, which could be much more efficient because Sonic is actually quite efficient when it's not in the fully succinct mode compared to Planck and Marlin. So another thing we could do, for example, is we could actually switch and move to a different curve cycle. So instead of this MNT4, MNT6 cycle where both curves are pairing friendly, we could switch to a different cycle where we have a BN curve, which is a prime order curve, which forms a cycle with another prime order curve, a 381-bit curve, for example, which isn't pairing friendly. And then over this non-pairing friendly curve, we could use any proving system. We could use bulletproofs or whatever. Now, naively, this would seem to be really expensive because the verification circuit for, let's say, Sonic or Gauss-16 or whatever you build on top of this pairing-friendly curve would have to do all of the expensive multi-exponentiation steps that are involved in verifying a bulletproof. So to solve that, we can apply the nested amortization technique. So we construct a variant of Sonic built on top of the inner product argument, which is from bulletproofs. And so it turns out it's pretty simple. This is something that's been done before in the Hyrax paper, where they essentially took a piece of the inner product argument out and created a polynomial commitment scheme with it. I think in that paper they were using multilinear polynomial commitments, but it doesn't really matter. You can use univariate polynomial commitments is what we need for Sonic. And so we can take this protocol, and it's actually proven zero knowledge and so on, and it fits all of the definitions and requirements that we need once you finagle it a little bit for Sonic. So what's really interesting is something I noticed is that this inner product argument is actually amenable to this amortization strategy. I go into this in the paper. I don't have enough time to explain it on these slides, but essentially we can apply the exact same amortization strategy that we do with the polynomials for Sonic with the actual inner product argument itself as well. And so as a result, we can create this helped version of Sonic, this amortized succinctness, without a trusted setup using the inner product argument, using Sonic on top of this inner product argument. So as a result, you can go back to our pairing-friendly, non-pairing-friendly cycle and build use Halo instead of this variant of Sonic, instead of bulletproofs or whatever, and you get a really efficient cycle that doesn't require the M&T curves. So that's just step one. It kind of allows you to avoid the M&T curve cycle. It's also, in a sense, it can be made fully succinct as well because the verifier of the Gross16 proof is constant. So the verification circuit for the Halo proof is also going to be constant size. So and with some other tricks, you can make this fully succinct as well. So this is an interesting step. But actually, obviously, the next step is pretty simple. We just build a curve cycle where neither of the curves are pairing friendly, and we use Halo on both sides of the cycle, and you get recursive proofs without a trusted setup. So in our paper, we actually constructed a curve cycle like this, a 255-bit curve cycle, which we affectionately call Tweedledum and Tweedledee. And these are specially designed to work with the Sonic proving system. But I mean, SEC P256K1 has such a cycle, and I'm sure you could avoid needing to design specific curves for Sonic. We just did this because we wanted certain endomorphisms to be in play, and we wanted large roots of unity so we could do polynomial arithmetic really efficiently. But so that's why we constructed our own curves for our proof of concept. So there's some more optimizations that go into Halo, which I'd love to talk about, but would take forever. Some of them are really interesting, like circuit optimizations that I think are really useful. So I'll just go through these real quickly. So during the verification of a Halo proof inside of this verification circuit, sometimes it needs to perform field arithmetic on a non-native field, the native field to the other proving system on the other side of the cycle. And so something that we do is we actually commit to these values, or we shuffle them in as public inputs to the other proving system, and the other proving system is responsible for performing the arithmetic and checking for us. So that's something that we do to avoid scalar arithmetic in the wrong, or field arithmetic in the wrong field. We also don't use the full challenge space because when you're verifying these inner product argument proofs, the challenge space being extremely large, it's the full size of the field, is not necessary, and it's really expensive. We have to really conserve as many gates as possible. So on that point, we come up with several optimizations where basically instead of mapping a challenge, a 128-bit challenge as a scalar and performing a point multiplication, instead we map the challenges to special scalars in a still quite large challenge space that can be very efficiently computed using an endomorphism inside the circuit. And we actually use a similar strategy to accelerate Peterson hashes, so we have a more efficient version of Peterson hashes over sapling, which we use inside of our proof of concept. The inner product argument, the verifier needs to perform multiplications by squares, so we hash directly to the squares, using some things that cause some potential soundness problems that I think can be fixed. But so we're being very aggressive in coming up with these ridiculous optimizations to eke as much performance out of this as possible. And then this last point, which actually hasn't been implemented yet, but we can actually collapse all the inner product arguments inside of the verification circuit into one, and that gives you a huge boost in performance as well. So I don't have a slide for this, but the actual performance numbers for Halo, I don't have them yet, but I think the proofs will be around 10 to 15 kilobytes, and will take, I don't know, depends on your hardware, but seconds or less than seconds, or less than a second maybe potentially, to verify a recursive proof, which is really good. But of course that requires potentially a multi-threading on your machine. The proving time is actually really competitive with, let's say, Fractal or whatever. It's been the benchmarks that I've seen. So conclusions. Like I said before, there's a number of different techniques that we're using in Halo. The most interesting technique is this nested amortization strategy, which I think is really useful. I think you can use this to improve all sorts of different protocols. Halo achieves recursive proof composition for the first time. That's obviously debatable because we haven't really provided any security claims, so you don't really know what we've achieved. I claim that we have, according to some abstract definition that's in my head of what we've achieved it. Like I said, the nested amortization technique is useful for other things, for example, the MNT curve cycles, where you can avoid the MNT curve cycles. But then also, for example, if you wanted to use Fractal to achieve recursion and you didn't want to use Halo, for example, Halo is still very useful because the Fractal verifier, for example, can check a large number of these Halo proofs and use the nested amortization strategy so that the proof size is much smaller, because Fractal proofs are quite a bit larger than the kilobyte size, lower bound or so of Halo proofs. The batching technique that we came up with for the inner product argument isn't just something for Halo, it's something you can use to accelerate bullet proofs. So a lot of people are really interested in that, and I hear about it a lot. The tricks that we're coming up with for the circuit using anamorphisms and all this other stuff, I think will be really useful as people consider building public coin interactive protocols and Fiat-Shamir implementations inside of verification circuits. I think these kind of tricks will come in handy for protocols that do that. I think we're one of the first protocols that are beginning to actually implement this sort of thing in practice using elliptic curve arithmetic. Like I said, faster Peterson hashes, these interactive strategies between the proving systems are really interesting, and I think that opens some doors for some performance improvements. And that's about it for me. Thanks.
Cool. All right, I think we have time for like a few questions. We are pushing a little bit back. Georgios, we can get set up in the meantime. But if there are any questions or comments, I'll leave it for a moment. Anyone? Oh. Do you want to?
Hi, sorry, this is a bit of an odd question, just because my memory is really bad. The Tweedledee and Tweedledum curves, are they twisted Edwards curves or short Weierstrass curves?
The short Weierstrass curves, yeah.
Cool. Nice.
It wouldn't be possible to make a curve cycle with twisted Edwards curves because they would, the cofactor in the Haas-bound. So.
All right. Are there any other questions? Okay.
In the recursive step, the circuit, the predicate, is it growing like an iterated log?
Is it what? I'm sorry?
There looks like there's some iterated log growth. It would be small, but so every time you have the log size circuit, then you get some new log size components. You do the recursive step where you prove that you've run the verification circuit. Do you not get the growth of that circuit to be like an iterated log?
No, the circuit stays the same size at every depth.
Precisely the same size, not even an iterated log. Like log of n plus log of
No,
n
yeah,
plus.
it's the exact, yeah, it's the same size at each step of the recursion. It doesn't change at all. There's no additional state or anything. It's just the same size.